So as was already mentioned, my name is Emmanuel Charleson Dapaah, and in collaboration with Professor Grabowski, I'll be presenting to you my research on the topic, a model-driven root cause analysis for trustworthy AI, a data and model-centric explanation framework. So to begin with, I'll walk you through the presentation outline, where I'll first give an introduction and motivation to this research. And then we will discuss the methodology that was employed, and then I will interpret some of the results, and then I conclude this presentation. So to begin with the introduction, in the world of machine learning, in a situation where you probably want to perform a classification task, there are two main components you would need, which is your training data and the ML algorithm you want to use. And once you have these components, you can then train your model on the data. And based on that, you will then achieve a predictive model. And when you have your predictive model, if you've done any form of model training, you will realize that your model is likely to find itself within two major categories. It is either your model is generalizing well to the unseen data, or your model is not generalizing well. And in the case where your model is not generalizing well, this could also either be the case your model is either underfitting your training data, or your model is overfitting your training data. Now, to discuss each of them into a bit details, when we begin with the situation where our model generalizes well to unseen data, I want us to discuss this from the perspective of complexity. So, when we say our model is generalizing well, in the domain of complexity, this implies that we have a data whose complexity complements the complexity of the model. That is, the data is not too complex for the model, neither is the model too complex for the data. And in so doing, when we train the model on this data, we are able to learn the underlying pattern in the data. And for this reason, when we introduce unseen test data, we are able to achieve a high test accuracy. When we come to the case where the model does not generalize, in the situation of underfitting, still looking at it from the perspective of complexity, this is where we may have selected a very simplistic model up against a very complex training data. And in so doing, during our training process, the model is unable to learn the underlying pattern in the data. And as a result, when we introduce unseen test data, this then leads to a low test accuracy. A similar pattern also happens in the case of overfitting. But then in this situation, this is where we have a more complex model up against a simple training data. And in so doing, during our training process, the model begins to memorize the data points in the data, even including the noise within the data. And as a result, when it receives an unseen test data, it also gives us a low test accuracy. And in all of these three categories in which we can likely find our model, there is one question that still lingers in the minds of researchers or practitioners. And that is, if I have my test accuracy, what is actually driving the test accuracy? Is it as a result of the data complexity or the model complexity? Because as I explained earlier, in the case where your model is generalizing, this means the data complexity and the model complexity complement each other. But then which of these is actually driving the performance accuracy we are observing? Also, in the case where the model is not performing well, we want to understand which of them is actually the driving factor, so that this can help us to make a more intuitive and also guided debugging of our model. So to answer this research question, we propose what we call the root cause analysis model. And for this root cause analysis model, it will take as an input the data complexity and the model complexity. And with the data complexity, we would consider certain specific complexity characteristics or meta features of the data. And with the model complexity, this will be characterized by the hyperparameters of the model. And this will be fed as inputs to the root cause analysis model. And then the model will then try to learn a mapping between the data complexity and the hyperparameters up against the test accuracies that is being achieved. And when this model is able, the root cause analysis model is able to learn this underlying pattern, then we can go further to give a breakdown attribution to how each of these complexities from the data and the hyperparameters are actually contributing to the performance accuracy or the test accuracy we are observing. And this is the model we want to use to try to give a trustworthy explanation of our test accuracy. So in the next slide, I would discuss in a bit details how the methodology we employed in order to design our root cause analysis model. So for the methodology, we selected 270 classification tags from the OpenML database, which characterize a diverse real-world examples of classification tags. And for each of these classification tags, we extracted specific complexity meta features. And the complexity meta features we looked at were three major ones. The first one being the imbalance, the class imbalance of the data, which gives us information about the distribution of samples in each class. Then we also looked at class overlap, which tells us how data points of different classes lie together in the feature space. And then the last being the data sparsity, which tells us how dense the data points are distributed in the feature space. These three complexity meta features are well studied in the literature and are known to characterize the complexity of a data set. And so for this, we consider these three. And for the model we use for our case study, we considered a decision tree. The reason being a decision tree is already explainable, so we can then be able to intuitively also know if whether our root cause analysis model is performing as expected, so that based on that, we can then generalize to other models. And for the decision tree model, we selected 300 hyperparameter configurations of the model. And we focused on three key hyperparameters of the decision tree, being the max features, the mean sample leave, and the mean sample split. And these are three hyperparameters which are well studied about the decision tree, which is known to characterize the complexity of a decision tree model. And with these in place, we then train each of the 300 configuration on each of the 270 data sets, and then we record the accuracy. And in this situation, we recorded the balance accuracy of each of these combination. And once we have this in place, we then form what we call the metadata set. So the metadata set, at the end of the combination, we had 81,000 instances. And the metadata set comprises a combination of the data complexity against the hyperparameter and the corresponding balanced accuracy that was achieved when it was trained. And then we feed this metadata set into an explainable boosting model, which is an additive model with high fidelity to help us to be able to decompose our balance accuracy to show which of the data complexity and hyperparameters how they are and to show how they are actually influencing the balance accuracy we are observing. So our explainable boosting machine is what we would be using as our root cause analysis model. And this gives us then a pictorial view of the methodology we employed in order to design our root cause analysis model. So then we move on to an example, and then based on that, I would explain the results that we obtained. So even before we have a discussion on how we can use the root cause analysis model to be able to perform this attribution of how they are contributing to the performance of the model, we first wanted to know how well the root cause analysis model is performing. That is the model fidelity. And based on that, we split our metadata set into a train test split of 80-20 ratio. And then we trained the explainable boosting machine to see how well it's performing. And then based on that, we observed the R squared metrics and also the mean absolute error. And we realized that our model was able to give us a good performance metrics. That is, we can conclude in this situation that our RCA model is able to achieve an accurate mapping between the data and hyperparameters in corresponding to the observed accuracy. And in so doing, we can then trust whatever attribution our model will be giving us in this case. So now, for the purpose of this presentation, I'll just look at two simple examples to explain how our RCA model performs its attribution. And we begin by a success case, and also we look at a failure case. So In a success case, we have two different data sets, one being the qualitative bankruptcy data, which looks at how a classification data set to predict whether a person will be bankrupt or not. And when we train this data on a specific configuration of the model, we achieved an accuracy of 90, a test accuracy of 98%. And with the example of the failure case, we had the IBM employee data set, which is a data set, classification data set to be able to classify if whether the performance of employees. And with a specific configuration, we had a performance of 48%. So for each of these data, we extracted the data complexity meta features. That is the class imbalance, the class overlap, and the data sparsity. And by comparing both of them, one thing we can observe is that in the success case, we see that the complexity of the data is relatively low because the complexity is bounded between 0 and 1, where higher values implies that, or values closer to 1 implies that the data is more complex, and lower values means it's less complex. So here we can see generally the data complexity is low, whereas for the failure case, we can see that the data complexity is relatively higher. But then it's also worth to note that data sparsity remained the same in both data sets. And for each of the data sets, we had a unique hyperparameter configuration that also contributed to the performance that was achieved. So now beginning with the success case, we want to feed this information into our RCA model we have trained, which is the explainable boosting machine. And based on that, it should give us an attribution of how each of these matrices or factors are influencing the performance we are getting. So when we feed this into our explainable boosting machine, what we observe is that class overlap is the main driving factor of the good accuracy performance we are observing, whereby it is contributing 17% to the improvement of the model, followed by the fact that we have low class imbalance and also the data is dense. So this shows that the data has a low complexity, and this is what is driving the performance that we are observing. But it's also interesting to note that our root cause analysis model is able to identify that the mean sample leaf, which is currently configured to be 14, is actually reducing the performance by 1%. And this and the interpretation we can also deduce from this is that this implies that if we want to actually push the model's performance a bit further, probably into the 99%, then we stand a better chance of trying to optimize the mean sample leaf hyperparameter. So this is an information that we can deduce from the decomposition of the root cause analysis model. And so to try to summarize the success case result, our root cause analysis model is able to give us information revealing that the root cause analysis model is telling us that in this success case, the success is driven more or primarily by the data, whereas also specifically it is the presence of the low class overlap and imbalance in our data is what is actually explaining the performance we are actually getting. Now coming to the case or the failure case, here we also feed this information into our root cause analysis model, and it tells us that the main driving factors leading to we having a low balance accuracy on the test is as a result of the high class imbalance as well as the data sparsity, telling us that these are actually reducing the performance by 7% each. So in this situation, it means that when we want to actually improve the model performance, rather than doing a try and error of try to either do optimization or do other kind of data pre-processing, we have to focus more on the class imbalance and the data sparsity. Our result also shows that the hyperparameter is also a driving factor which is reducing the performance, and specifically it shows us that we need to try to improve the max features, because intuitively when we look at max features we can see that max features is actually low, meaning that we are only considering only 20% of the features during a split. So our root cause analysis model is able to identify this, so in so doing we can actually improve max features to improve performance. It is also worth noting that our model is also able to capture interaction effects between the data complexity and the model complexity, where it shows us that the interaction between the max features hyperparameter and the class overlap in the data is also a driving factor to why we are actually having the low performance. And in so doing, we need to pay attention to the data complexity, which is the overlap, as well as the max feature hyperparameter. And also, to summarize this result, our RCA model highlights that for this failure case, our focus should be on trying to reduce the imbalance, as well as doing some form of feature selection in order to reduce the density of the data in order to improve it. And it also gives us information that the restrictive configuration of the max features is also contributing to why we actually have a low performance. So these are two simplistic examples to show us how our root cause analysis model is able to decompose and explain how the data complexity as well as the model complexity is contributing to our observed performance accuracy. So to conclude, we can conclude that we have been able to propose an root cause analysis model that is able to identify and also help practitioners to be able to decide if whether in a situation they should go for performing a root cause analysis, they should go for performing a hyperparameter optimization or data pre-processing, because most often in practice, this is done as a form of try and error, or either by the expertise of the practitioner. But then with this root cause analysis, this gives us a guided approach to be able to either go for optimization or go for data pre-processing. It also bridges the gap between data complexity and model complexity, because if you look into the literature, most often data complexity and its influence on model performance is studied in isolation from models complexity influence on model performance. But then with our RCA model, we've been able to bridge the gap where we are able to show the relative influence of both the data complexity and the model complexity on the performance of the model. And in conclusion, this also helps us to enable transparency and accountability, because most often when we have a high performing model, we wonder, okay, what exactly is causing this model to perform as it is performing? And also when our model is performing low, we are really unable to really explain why this is the case. But then with this root cause analysis model, we are then able to be confidently account for why we are having a specific test accuracy or a low test accuracy. And as our future work, we intend to perform a controlled perturbation experiment to verify our attribution validity. That is, if our RCA model points to a particular hyperparameter either being the cause of why we are having a low performance, then we want to perturb this by trying to improve it to see whether we will actually get the gain our RCA model is suggesting. And also, we would, as our future work, we would want to integrate this RCA model into automated ML pipelines to help us to be able to do a real-time interpretability or to help us to do a real-time interpretable debug. And that is, as we train or build our pipeline in a situation where now our data is becoming more complex, or our model is becoming more complex, our RCA model will be able to give us a real-time information, and based on that, it guides us on how to debug our model to improve performance. So this basically sums up our research, and I would like to conclude here and thank you all for listening to this presentation.